We are asked to give the molecular geometry of the following molecule. The first step in doing that is we have to determine the number of electron groups. To do that, we're first going to tally up electrons. So Te gives us 6 electrons. There's 5 fluorines, which gives 7 each. And we have to remember that there's a minus charge. That's going to give us an extra electron. These tally up to 42 electrons. The Lewis structure is going to look something like this. Five fluorines present. We're just going to distribute our electrons to the fluorines. Now you're going to notice, once you're done distributing the electrons to the fluorines, you're going to have 2 electrons left over. So we have to assign those to the central atom. That's going to break octet. This is also an ion, so you have to make sure to include that in both structures. You're going to notice that there's 5 bonding pairs of electrons, and there's 1 lone pair of electrons, giving us a total of 6 electron groups. Now, given the fact that we have 6 electron groups, there's 3 possible structures that can fit our molecule, which are all going to be octahedral. The one with 1 lone pair is called the square pyramidal, and we'll draw that on the next slide. And to get the nicest drawing for the square pyramidal structure, you want to start off by drawing a box and put your central atom inside the center as much as possible. You're going to put your fluorines in the corners. The 5th fluorine is going to go straight up. Note that the central atom and this fluorine are the only ones that are on the same plane. After distributing our electrons, we're going to show these 2 fluorines on the bottom wedged out, coming out towards us, out of the plane. And we're going to show these 2 going away from the plane. Again, as with the Lewis structure, we're going to have an extra lone pair for the central atom that's going to go down here. Now, if this were just a standard octahedral, all these angles would be 90 degrees. Because we have a lone pair on the bottom, we have to remember that lone pair bonding pair repulsion is actually greater than bonding pair repulsion. Now, what this means is that the repulsion between these fluorines is actually going to be weaker than the repulsion that these fluorines experience from the lone pair here. This is going to cause the molecule to bend upwards away from the lone pair in this perspective. So we're going to label this as less than 90 degrees. There's another angle that's not visible in this perspective, but we'll show it in the following slides, is that it actually goes around the plane between this fluorine and this fluorine is at 180 degrees, but that's not a significant angle for us. We're more concerned with the 90 degrees between the fluorines above the plane. This structure is called the square pyramidal. And this is the corresponding structure anytime you have 6 electron groups with 1 lone pair. So 5 bonding pairs and 1 lone pair. You would use this shape here. This is a program generated image of what we just drew. As you can see here, there's a bend on the angle that we were talking about. This is actually more than 180 degrees, but you can see that these are slightly smaller than 90 degrees. It's going to be greater than 180. If we were to label this, our Te would be here, and all of these would be fluorines. And you can see our lone pair here, causing the bend. And again, all 6 electron groups are visible here. 1, 2, 3, 4, 5, plus the electron lone pair. We're going to repeat it again just for the sake of memory. Lone pair, bonding pair, repulsion is always going to be greater than Sorry, can't see that. Bonding pair, repulsion. So that's always going to explain the bends in the molecules. Just keep that in mind, and you're always going to know which molecules bend and which molecules don't. And you'll also be able to use deductive reasoning to find out if angles are less than or greater than the counterparts with no lone pairs. I've also included another diagram, a system-generated molecule, the same exact molecule that we've been working with. And notice here that it says selenium. That's actually not selenium, it's actually Te. It's just not in the program, so that's how we used it. So again, this is the same molecule. You can see the exact same angles here. These are all going to be less than 90 degrees. The big one over here is going to be, you can't really see it very well. This would be greater than 180 degrees. This is the model kit representation of our molecule. We can just label it just the same. You can see our lone pair here. Well, I'm going to include another picture of this with the perspective that we've been working with, so we can just see it in the same angles. This is how we drew the molecule. I wanted to show it in this way, just so you can see that what would normally be the equatorial angles and what would normally be the axial angles. It actually doesn't matter with these molecules that have 6 electron pairs, as all the angles are the same. So we arbitrarily chose to remove this one, but we could have actually removed any of these. Doesn't matter where. If we were to remove one of these, we would just turn the whole thing over, and it would be equivalent. Now again, with model kits, you can't really show the bend of the lone pair. So all these appear to be 90, but again, we need to remember that lone pair, bonding pair, repulsion is greater than bonding pair, repulsion. And that'll tell us that our angles are less than 90 degrees and they actually bend away from the lone pair.